Good morning. This is your stat sensei, Mr. Spensei, and we're going to look at an exit ticket on central limit theorem, and we're going to go back to an old problem on IQs. So in general, IQ scores are known to be normally distributed. That's key. It's very important, with a mean of 100 and a standard deviation of 15. So we're normal, mean is 100, standard deviation is 15. A random sample of 100 IQ scores were taken. Well, this is okay. So we have a random sample of 100. Using the graph below, apply the central limit theorem and the empirical rule to graph the scenario. Be certain to label the z-scores and the standard deviation of the sampling distribution of the mean. So they want us to use the standard deviation of the sampling distribution of the mean. Well, the standard deviation of that is the standard deviation of the population divided by the square root of n. So in this case, 15 divided by the square root of 100, so that's 15 over 10, which is 1.5. So the standard deviation of the mean is 1.5. But the mean is the mean is the mean. So we're going to be using this standard deviation and this mean for this situation. We're working with central limit theorem and the sampling distribution of the means. All right, first off, our z-score still doesn't change. It's all z-scores regardless of the situation. 0, 1, 2, 3, -1, -2, -3. And we still have 68%, plus or minus 1, plus or minus 2 is 95%, and plus or minus 3 is 99.7%. So that didn't change, even though our standard deviation is different. Our mean is the mean is the mean, so our mean is still 100, but our standard deviation is now 1.5 as opposed to 15. So we end up going 101.5, 103, and 104.5, adding 1.5 as we go up, taking away 98.5, then 97, taking away the next 1.5 is 95.5. So earlier when we did this, we had a standard deviation of 15. But now our spread is much less. And our spread decreased because we increased our sample size, and individuals are what's located on the one prior, standard deviation of 15. But here we're working with a group, and it's much less likely to have a group with an IQ that high than it is an individual. All right, so we're going to be closer to the actual mean as we increase our sample size. So what is the upper and lower bound for plus or minus 1 standard deviation? Well, lower bound is 98.5. Upper bound is 101.5. For 95% or plus or minus 2 standard deviation, it's 97 to 103. Lower, upper, lower, upper. Plus or minus 3, 95.5 to an upper of 104.5, lower and upper. And what percent of samples have a mean that will be greater of 100? So sample size of 100 with the mean greater than 100. Well, that's still just shading up And remember, it's symmetric, so the mean and the median are the same. So this is still 50%, which is what we had on the previous one, because 50% is still above the mean, it's still above the median, because they're equal, because they're symmetric and mound shaped. But here's where we're going to get a great difference. On the prior one, when we did a norm CDF for a 120, it was 9% had a IQ above 120, an individual. But the probability a group will have an IQ greater than 120 is not going to be very likely. So we're still going to look at this much the same way. We're going to do this by a norm CDF today. So norm CDF, and we're going to draw a picture of it. Our mean is still 100. Our X value is 120. As a reminder, our standard deviation for X bar, because we're working with means, is 1.5. So lower bound, 120. Upper bound, positive infinity. Mean, 100. Standard deviation is 1.5. So this is my lower, this is my upper, this is my mean, this is the standard deviation of X bar. So let's run that on the calculator real quickly. Now, there's other ways to do this on a calculator that are more convenient, but just so that it'll be the same for today. Second vars, normal, CDF, lower is 120, upper is infinity, mean is 100, but our standard deviation is now 1.5. And we end up getting, we need 3 zeros in front, so 0.0007. That's much less than 10%. We were at 9% here, 0.09, which is 9%. And this is 0.07%. Very, very unlikely. I want to show you one other way to do this using the calculator, because this will be the way we normally do it. And that's going to be stats, test, z-test. So stat, test, z-test. We're going to highlight the word stats. Our mean is 100. The population has a standard deviation of 15. The X is 120, but our sample size is 100. And we're going to shade up. And there it is, 0.076007. So we get exactly the same answer. It's a different way to approach it. Would it be okay to use the distribution of means if the sample size had been 10 instead of 100? Well, remember, we gave a rule in class that said to use central limit theorem, the underlying distribution had to be normal or the sample size had to be a 30 or more. Well, they want to know if it could be 10. Well, here they told us the underlying distribution was normal. So since it was already normal, we could. So the answer is yes, because the underlying distribution is normal. I'm going to go ahead and add something else. If it were not, then, so if it were not normal, then we would need a n greater than or equal to 30. In other words, a sample size greater than or equal to 30 to use central limit theorem. All right. Thank you for watching, and I will see you on the next one.